Hello, and welcome to today's webinar. Our speaker, Dr. Moshe Ben-Talila, has over 14 years of experience as the manager of VisiMix's customer support. He holds a BSc and an MSc in chemical engineering from the Technion, specializing in reactors design. He also holds a PhD in chemistry from the Hebrew University of Jerusalem, with his dissertation focusing on practical methods for scalar processes in the chemical industry. Dr. Ben-Talila has extensive expertise in technological transfer, having worked as a pilot plant manager and project manager in an API company for over 15 years. Dr. Ben-Talila has made significant contributions to the field, including his involvement in developing a BSc degree program in pharmaceutical engineering and writing the syllabus for the Pharmaceutical Engineering BSc degree program at the Azrieli College of Engineering in Jerusalem. He is also a lecturer at the college, teaching reactor design and principles of fluid mechanics. The topic for today's session will be improvements of safety characteristics in stirred reactors. During the session, feel free to ask any questions in the chat box. We'll do our best to address them either during the session or via email afterwards. So we hope you enjoy today's presentation. And without any further ado, I'll hand the microphone over to Dr. Moshe Ben-Talila.
Okay, so thank you very much, Marcy, for your introduction. I hope you can hear me. And if you have any question, please feel free to write your question in the chat. We will like to answer you during the meeting or after that. If you are interested to contact us and to have a tailored presentation for you, please contact us. And we're very happy to fix the time and progress. Today, as a part of our forum that we have frequently 1 to 2 months, 3 months, depending on the topics and depending on the program, we'll discuss more about some topic that it seems to be a different topic that is not so mainly mixing, but what we try to give you is how, by taking in consideration some results that the software can provide to you, you will be able to be part of the group that is studying the hazard operation and the hazard in any process and how to be in the good mixing practice. So VisiMix, at the beginning, we'll talk about a few minutes about the company. If you're new, if you want to know more about the company, so 5 minutes for it. VisiMix is a company located in Jerusalem, in Israel. We develop simulation of mixing processes for the industry, and we are continuing to work in the same way that always, even if we have some internal problems here in Israel, and we are doing our job during many years to have and to contribute and the civilization to progress and not to destroy it. So we like to progress and continue to work in this way like we did during many years in all the technologies that we develop in Israel to all over the world in order to be a better world. In our specific topic, we'll talk about inherently safer design in sterile reactors by VisiMix, but it's not only the design. We are talking about a safety process and how to use the mixing unit operation in a proper way, and how to take in consideration this mixing operation during our activities when we're talking about any kind of process that can degenerate after that in some safety process problems that we can avoid and we can consider before they will happen in our time. This idea was promoted by Dr. Yuri Nehamkin, And with the help of the software that the developers were Professor Loris Braginsky and Dr. Yuri Kokotov, they developed this concept coming directly from the outputs that VisiMix are providing to you. So we'll talk some minutes about the company. We will have some introduction or motivation why we're doing this kind of thing, VisiMix products, and after that, main kind of examples that you can illustrate what we are talking about. VisiMix is a unique software because it's based in physical models that we solve in order to know the velocity of the flow. You can connect it with your process in order to understand what was the environment you generate to the materials to interact and to generate your products. And in order to generate the velocity or to calculate the velocity, we need to take in consideration that this result will be relevant and representative. So in the models of VisiMix, we are taking in consideration a very deep study about the mechanical fluid in the empirical point of view in laboratories, and we detect the phenomena that happen in steel vessels in very scientific part, deeply about friction factors and more. And we introduce this knowledge as a part of the model that we solve. We're talking about semi-empirical models that take into consideration the physics that happen into the tank in order to provide to you the results. Everyone can use the software. We show to you in a few seconds how we open the software, how we feed data. And once you are using this software, because it's simple to use to everyone, you will be able to improve the understanding of the process, because we are taking in consideration a phenomena, unit operation, that's mixing, that is serving any process or any interaction between materials. The software was developed by Professor Loris Braginsky and his team. They developed this software when they were in Russia, the model, when they were in Russia, and they needed to provide to the government in Russia answer about what will happen with the process in the next step, the meaning of this in design or in transfer technology or in scale-up. And in order to do it, they develop a model for themselves that describe the mixing into a tank. This model is our model, okay? This is a unique one. In order to solve it, we use the numerical methods to solve differential equations. We use empirical data in order to be sure that it's relevant and representative. And this is what they developed. Once they came to Israel, we transfer all of this knowledge in a software package. And during the years, we developed more and more software. We have now more than 10 products that support the chemical industry in order to transfer technology and to be sure that the process is safe and you can progress in this interaction a good way. So this is the summary of what VisiMix is doing. We solve the momentum balance. We know the velocity of the flow. We know this velocity by combination of theories, fluid mechanics theories, and empirical data. And once you know the geometry and the density and viscosity of the media, you will be able to calculate this velocity. But if you include other inputs, you will be able to know what is the solid distribution, the drop size, the heat transfer coefficient, and more. All of them are mechanical stability of the shaft. All of them are part of the safety process. Because if we have a process that we didn't take in consideration solids are in the bottom, we can start to have some accumulation of material, after that some exothermic reaction. Okay, of course, exothermic reaction we need to control by feeding or by a cooling system that will be enabled to do it. If we have a separation of phases and we didn't progress with the process and we progress to the next step, and during the next step we have some kind of dangerous situation, so we need to take care that my process is good mixing practice. It's going in the way that will be representative and will provide the conditions to process. So this is the main idea, taking consideration that it happened. In the software, we have a warning message that are explaining what we are doing. And this is the main part of the focus we will do. I will show you examples about it. Companies working in this field, as you can see, in every field, can be pharmaceutical field or chemical specialty field or polymerization or oil, agrochemicals. any kind of material that we are using with steel vessel will be enough to use the software and to try to save problems in operation, in quality, in productivity, and of course in safety. That is our topic. And Professor Dr. Victor Timoben was one of the experts. You can see more of them in our more of this explanation from these expert people in our website. Please come there and navigate inside our website. So this is about the company. Now let's talk about our field. The reason that that this topic is so important is because when we are transferring processes from one stage to other stage, and it can be we're designing equipment or we're transferring to other site or we are doing the scale up, we need to take in consideration that the geometry, even if the same process with the same raw materials and the same method and the same procedure, once we are transferred to the other side, because the geometry is different, the design is different, it's big equipment and so on, the hydrodynamic that we're generating is different. The meaning of this, the interaction between the materials that we want to interact in order to generate our process will be in different way, and it can generate deviations. This deviation can generate problems in safety, in operation, in quality, but maybe in safety, mainly in safety. So with the message we have with the software, we will be able to improve the safety process into our activities. So we're able to describe in three main expertise: the design, the operation stage, and we will investigate maybe some incident that happened. So these will be the three examples that we'll talk about, but it's taken from the main message that with the mixing, you are generating conditions to the materials to interact. And when the conditions will be a little different, it can degenerate in problems that will be touching and talking and taking giving us the scenario that can be problems with the safety. This is the main point. We're talking about steerer vessels, and if we do some brief literature survey, we understand, or literature investigation we collect, and we know that 14% of all accidents in chemical process industry, with 71% of them related to batch and semi-batch reactor operation. So we're talking about big quantity of problems, and we know from time to time, we hear from time to time, some explosion in one place, some problems with other place in the industry. And when we collect what happened, it happened maybe mainly in steel vessels, batch or semi-batch. Inadequate process analysis or heat transfer, we talk about 23% of the cases. Problems with reactions that are related to foaming and other kinds of things, it happened about 23%. And process contamination and cross contamination that continue to have problems in the safety is about 16%. So we have a very vast things that we need to take in consideration. So our concept is to introduce some kind of safety design or operation technology concept, and the way is to identify ways to eliminate hazard associated with the process, rather than to develop add-on barriers to protect people to this hazard. They were taken from one of these from a handbook of inherent safety, safer design. And the main idea is to include it in the knowledge. When we are developing process, we are designing, we want to take in consideration these warnings in order to be not in the range of work that will be dangerous. We have different kinds of products, and we can discuss about it more later. The point is that I want to tell you with this product that you can cover every mixing equipment with the combination of this kind of processes, product that we are offering for you. Of course, depending on the company, depending on the mixing characterization you have, you will use different kinds of software. In any one of them, you will get always the warnings that I will explain. We'll use one of the software, but in every one of them, you can talk about it. You can get this kind of warnings and take care, because these help us a lot in order to provide the information required for you. Which kinds of parameters we're able to calculate? Every parameter related to mixing and that define the conditions we're providing to the process to interact the material that we have in our tank. So if we talk about basic mixing information, is main mixing characteristics, vortex formation, flow dynamics, turbulence shear rate, stress, and on. When we talk about blending, we're talking about mixing tank in different levels. Remember, we're talking about fluid elements that are interacting in different zones, and we need to define the direction that will be good for the process. So all of this, we're able to calculate and provide numbers, not only descriptions, numbers that are defining exactly how far I am from one place to other place. And then when we are outside the range of work that will be good mixing practice, we will get a warning related to the parameters. When we talk about liquid solid, we talk about not settling materials or distribution of solid that will be not enough good, or will require more than the mixing power that we have in our vessel. And we talk about dissolution. It will be possible to have complete dissolution or not. All of this included into the software. We talk about leaching, liquid solid extraction. We talk about collision between particles, mass transfer coefficient. In the crystallization, we talk about uniformities, non-uniformity. What happened with the solid that we are getting out, and what will be the particle size. Maybe it's not good for us. We have some problems about a very thin material that will generate the next step that will be not possible to filtrate in a good way, and we accumulate some other liquid that maybe is dangerous. In the liquid mixing, we're talking about emulsification, and you know it is not simple to generate emulsification, and it's depending what we're looking for. If you want to generate a cream, you need a complete emulsification that will never separate after that. If you want to have separate phases into your tank, it's opposite. We need to separate phases, so we need to have enough shear rate to break up the drops in small drops. But after we stop the mixing, we will be able to connect between the phases and generate the two phases again. So there are two completely different ways. And if we are doing a process when we want to separate phases and it is not possible to separate, or opposite, we start to have to think, okay, it is not working well. Me can generate the generating problems about the safety and how to connect it, foaming and more. So you can see all of this, and this presentation will send to you on the video. You can see more and more parameters that we're able to calculate. Selectivity of reaction, local concentration of reagents. It is very important for processes that maybe we are accumulating reagents and after will react in instantaneous flow. So we have very heat release, and how to collect this heat release, will be possible or not. And take care that we are talking even on the mechanical reliability. The point is how, what is the shear, that the stress that we're applying to our shaft, and sometimes happen that this is more than the shaft is able to get, and we have a deformation of the shaft, maybe breakup of the shaft, and it continues to be a very important issue that we need to take care, because if we have in the middle of reaction and we're in this way, in this situation, we have really a very big problem. We have not mixing, accumulation there, how to manage all of this. We will be able to do what is the shaft that is important for it. So as you can see, we have many things to do. Of course, thermal safety is the main known. And of course, I will show the first example. We'll talk about analysis of runaway reactions and how to take in consideration overheating, overcooling, and how to do it in the software. Okay, after we finish what we're able to do, we can show what are the warnings that we are providing into the software. And this is the next step. We know that we're able to calculate. We know that this software is really relevant and representative. And we have an expert system of warning message that guiding our customer to be in good mixing practice. So what are the warning messages that we are providing when we are using any software that we have? You have, for instance, mixing power is too high to drive. We know that the reason can be that we have not enough power, so the viscosity or density of the media is higher than the design, and we don't use the correct power motor for it. And what will happen after that, that in some place or some time during the process, when we go more than the capability of the motor, maybe you have some stopping mixing because the plant was designed for the maximum capability, and you're going more than this. So normally companies have some safety overload, and when you are going more than this, the system stop, electricity goes drop down, whatever you decide to design your safety into the plant. So we need to take care more than this. If it is more than, so the power required is more, when you are moving the impeller, you maybe are you have problem with the vibration or with the stress that you are applying in the shaft, and it can generate to breakage the shaft, and it is really no good idea to have. Other point, for instance, the software tell you that you have a complete suspension question. What is the meaning of this? For instance, the particle size are big, or the concentration is so high. Okay, so what will be the hazard potential that we can have here? When we have this situation, we can increase. It can happen that it increase the bending moment in the shaft that we explained before that. Maybe we are plugging the bottom, continuous or batch, or batch. It is a problem because after that we need to take the material from the equipment, and it will be not possible to do it. And if my material is the reagent that is solid that I feed there, but my solid is in the bottom, in some stage in the process, maybe the solid start to be consumed. In some place, start to move into the tank. So it will be order of magnitude better connection to the reagent, and maybe will react so fast that we will generate a very high release of heat, and the temperature will go up. So we need to take care. Other place, other warning that we have in the software: centrifugal separation of emulsion is expected. Addition baffle is advisable. Here, it's very important to understand that sometimes we think that we have a good distribution of liquid into a liquid when they are not miscible. But in fact, when we see the picture, we have all moving, but in the top of the tank, we have the lighter phase, and in the bottom of the tank, we have the heavy phase, because we didn't generate enough shear and circulation to include the dispersed phase into the continuous phase. Now, if it is a situation and we provide the conditions, but there is really no connection between the material that they need to generate the products, they can decrease the dispersion ability of the impeller, and they can you can unpredict the reaction. You think that you have some reaction and it's not happening, and you go to, for instance, you go to after that to quench, but the reaction was not happening. So you fit another material that you progress, and you can have a complete other kind of interaction between material that you maybe never think that will happen. Okay? So warning: vortex reach to the impeller is generating not stable flow. Some not stable flow. The meaning of this is that the level of the media is not static, it's moving up and down, and it can include increase the gas into the liquid. You can generate foaming. This foaming can generate a separation of phases. They can grow the foaming to a place that the reactor will not be able to take. Some very typical picture I have from some production of pharmaceutical material, that you see all the foaming in the plant, because it was complete gas. So when you know gas is many times more volume that the reactor is not able to take. If you go up, you go to the exhaust, and then you have another problem that it is occupied and you are generating some pressure. So all of this can happen. or after some minutes or some seconds, you go more or down the temperature that you define. It is for runaway reaction or for very good cooling system that is going more than you want. All of this we can do, and the answer of this that the reaction will not go in a good way, and if the heat transfer is not good, we go to very no good situation that we want to avoid. So this is the kind of message that we can have. Shaft vibration, the heat agent is not correspond to the temperature that we feel, and all of this we can generate by then in problem. So what we want to do now, okay, I have another point here. Okay, this we're talking here about insufficient mixing because the short circuiting flow in the impeller area. We are talking about continuous flow, and we're able to generate it for this kind of information for you when we are talking about continuous flow and you fit some pulse and you want to see how far you are from the ideal or mixing. So we define how far we are from the well mixed equipment. And all of this we provide. So now what I want to do is provide you some examples. We have 3 examples. I will cover every one of the examples by some explanation, and I will come back to example 1. I will open the software and show to you how we can use the software in order to calculate that I will show to you now. And in this way, I hope you will have a good idea about how is the operation of the software in this inherent safety process. So how to take in consideration the result of mixing and the warning we have in the company, the software, in order to include in your hazard operations and hazard process safety evaluation. The first example is talking about a chemical reaction. This is the equipment we use. You can see it's a completely industrial equipment. And what happened here, what we like to do in this example is tackling safety problem in sterile reactor, where at the design stage. What was the problem? The problem was this: the process was the following. The actual process is performed in 2 stages. The first one, initial heating, which start the reaction. It's very typical. You feed your material, you heat in order to go, let's say, to some temperature of reaction. After that, if the reaction is exotherm, you need to keep fixed temperature. So you need to maybe change the heating to cooling in order to keep fixed temperature as you want. Okay. So initial heating, which start the reaction, and subsequent cooling required to remove the excessive heat, so the heat released from the reaction. The heating is achieved by steam at atmospheric pressure supplied to the jacket. Very typical way to heat sterile equipment, sterile vessel in the industry. And the cooling was with water is 20 degrees. That is normal. We talk this water 20 degrees tower heat, tower water, not chill water, tower water. Because the equipment that we use in order to have temperature 20 degrees, the tower, you are feeding gas, we are heating water, falling the water from top tower, and in the way that they have some evaporation, you have extracted the heat from there, and you get a cool water. The considered process occurring in the cylindrical fluid buffer that I showed before that at 85 RPM. And we did some analysis about what happened at the beginning of the way, what will happen if we are not cooling, and after that, what we need to do, or what is the extreme point that we need to provide cooling, and more than this will be not recommended because we will have exotherm and runaway reaction. So the first step, okay. Another point that that happened in this process was that we have solids. So the first to be sure is that our solids are moving well into the tank. So we don't have some velocity that is below the velocity required to generate slurry in our suspension, complete suspension in our tank. And we have no deposition of solids in the bottom or in the top, depending on the density of the solid and the density of the liquid liquid stage. And the second task is to talk about the runaway conditions. All of this data we got from examples that have in the book of safety, health, and loss prevention in chemical process. In some course that have take data from the real life and try to analyze the students. So we take this data and use the software in order to fit a general result. In fact, what happens when you will start to run the process, you will get this kind of notification. You remember, complete suspension is questionable, or partial settling of solid phase may occur. The meaning of this, at the velocity we're working, it is not enough. We need to increase the velocity in order to be sure that the solids are moving well. So the J is a just suspension solid is the minimum in this case was 72 RPM. So they decided to be sure that all is okay. So they decided to go to 85 RPM. When you are going to this number, you will see that the complete suspension is affected. Okay, this was the first stage of this problem. This that you can see, complete suspension is questionable, partial settling of solid phase is occurred, and complete suspension is expected, is something that the software provides to you directly. You even don't need to ask. The software pop up the notification, and in this way you know that you are in good mixing practice. The second step is the follow. The heat transfer calculation performance for the first process stage, when we are heating in order to reach to a temperature, okay, we get this notification after 443 seconds have elapsed, the temperature falls outside the indicated range of process temperature. So the software, when you feed that, and you will see, you need to feed the minimum temperature that you accept and the maximum temperature that you accept in your process. In this way, when we calculate and we see that you are passing the limit, you get the notification how long time you get in order to go less than, let's say, 10 degrees or more than 140 degrees. This time is giving me the understanding that after here is a few minutes, I am outside my expectation, and it starts to be a good starting point to think about what we are doing, what is the design, or what will be the operation in order to avoid this situation. Not that if instead the outstream, the stream, another heating reagent. So if we use not steam, we use Dow term SR1, because we think that, okay, I will not use steam, I will use another moderate heating system. When you, for instance, use another cooling or heating system, the software tell you, okay, but in the range of work that you want to apply, this kind of material is not available for you. So it's not into the specification of the material that you can use in the jacket in order to control your process, because you are looking for a range of working temperature that this material is not good for you. So we are taking consideration the service you are giving to the process in order to progress or relating to mixing activities. So this is the reason that you will get this notification. And after that, once you feed the steam and you have the results, you can see here two results. This one is that after 8 minutes, as you can see, we go very fast. More than 80 in the example that I will show to you will be more than 140 degrees. And you can see that it's very typical runaway reaction. Okay. Sometimes it takes a few minutes. At my own experience, it takes about 12 hours. It was very low, go up, go up, go up. In some place after 12 hours, they explode and really happen. Sadly, it happened. It happened in the company. Nobody. We had big problems in materials, but no problems in people. People continue to live with no problem. But this need to avoid. This kind of situation is not acceptable for everyone in the industry. You need to go very far from it and not to try to control in this one. And you can see that the concentration of reagent go down because it's a typical runaway reaction. Based on this graph, we understand that after 4.5 minutes from the start process and initial parameters, the second stage were at 35 degrees. Okay, after 4.5 minutes, you can see we were at 35 degrees, and we need to be sure, and the conversion was about, after 4.5 minutes, the conversion was about 4.75, 85 mole per liter. So we need to be sure that if we start to see this kind of situation, we need to apply the cooling after really we start to work. Maybe it will be not possible to do, we need to find other way. But in our case, this was the situation. In order to avoid the problem, and we don't like to do it, but in order to avoid the problem, you see that at this stage, below 140 40 degree, we apply after 4.5 minutes, or after a conversion of 4.75 or 85 mole per liter, we switch it to cooling. And when we switch the jacket to cooling, we were able to avoid the runaway and to really start to go down the temperature. Of course, I advise not to go to this situation. You need to go very down, to try to control, to have more better cooling, and this is what we advise to do. Okay, so the duration of the cooling stage is about 5.3 minutes, and the total reaction, it was very short time. It is not advisable. Again, in industrial times, 10 minutes is nothing. So try to do more more extent. Okay, and it is possible to do. But in this specific case, in this specific equipment, it was the reason that we have this example, because it was not good, successful way, and it was an accident. Okay? So what I want to show to you at the end, how to operate the software in order to analyze this kind of thing, and how we can generate this kind of graph that show us how we can change the cooling system and generate results. The second example is a typical example that if you study reactors with Professor Scott Fogler, that last year passed away, was a very good instructor of mixing and in reactors. So we have another example about polyoxide generate propylene. Sorry. We consider the production of propylene glycol, PG, by the hydrolysis of propylene oxide, okay? And what happened here is that the exotherm here in this process was catalyzed by some process, and again, here we had process or scale up that happened when, by using the equipment so long time, we need sort of falling layer. What is a falling layer? Some layer that we build in the wall of the tank, okay? That when this falling layer is growing and growing, the capability to extract the heat from the wall of the tank in the process side to the jacket with decrease, and if it is decreasing, you are not able to extract the heat, and in some place, in some of the batches that maybe over 2 years or 1 year, you start to see that you are not controlling so much the temperature. So this is what happened here in this example. So we change the falling resistance, and we see how the pressure we need to run into the jacket start to grow down according to the falling resistance. That is the building of this thin layer that we have inside the jacket. As you can see, in some place, how the pressure is going up in the place that you are not able to progress. Okay, so this is the second example. And the third example, we were talking about the mechanical stability of the shaft. In this example, what happened here mainly is we generate some stabilization in a big equipment, and when we use this kind of structure of shaft, the process generate enough solids that generate problems in the loading of the shaft into the shaft. And you can see stiffness condition for the shaft is not satisfied, shaft vibration characteristics. So the software provides to you this, and the torsion shear was not enough. And what you can see immediately is how the critical frequency is about 1 per second, and you see that what we are applying is 0.412, and we calculate it with the material building of the shaft, the dimension of the shaft, and you see that we are over that 33%. And once we take in consideration another kind of structure of shaft and the other design, of course, now you see that our critical frequency will be 1.55, and we are applying only 0.42, so we are very far from the critical frequency. All of these examples you can find on our website, and we can illustrate them. For instance, if you see the example about polyoxide to propylene oxide to propylene glycol, you have here the complete example, and this example is in the website. And the other example about the another example about the heat release of the reaction, we have it, and it is in the website. So all of them you can see and go. So in conclusion of this, before I open the software, in conclusion of this part is that with the software, you will be able to have a process analysis based on justified technology calculation and understand the conditions applied to your materials. VisiMix software is giving you a capability to simulate different kinds of situations, solid liquid, liquid heat release, configure, understand the process in a good way, and it's very simple to use. I will show to you in a few seconds. And you can analyze in every kind of activities that you are working, because by then the company is expecting from you that you are the expert. What will happen with my process in the next step? So the meaning of this, they're asking you, okay, now I need more material. Please give me the design, how I will operate in this equipment, or I want to go to scale up which equipment is good for me. So all of this you can take in consideration, and you can show what can be the problems when you are using different kinds of equipment, and of course do this safety analysis and hazard analysis in a good way. And by unit operations, you can see how these lists, in our cases, were well explained and getting results from it. Okay. So from the here to the end of presentation is only the explanation about the pro, so I will not cover it. I only will send to you so you can read more about it. And what we wanted to have in the conclusion of this part is that the software is giving you a capability to understand the process. We provide all the information that you have in our website. We have examples about the use of the software in different cases, as I showed you before that. And taking account that VisiMix is a complete model. This is really a model, our model that was proved for many years and from the lab to production. And it is not a couple of correlations that you can find in the literature and put in itself. And it is not only a mathematical solution of differential equations. It's really a combination of expertise that we built during many, many years and want to share with you in order to give you better understanding of the process and consider a phenomena that happen in any case into the stereo vessels. So what I will do now is I will open the software and show to you how we can operate in the example number 1 that we discussed about the runaway reaction when we design a process. When we design the heating step and afterward the cooling step, and we need to be very careful about when we change in order to avoid problems. So what we need to do is I will come to the example. The example is here and we'll send to you, of course, with all the explanation about the input data we need to do. And now I will open the software and will follow exactly the picture that we have here, okay, the example that we have in the document. So the first to do is looking for the VisiMix turbulent software, and the first to do is project new, and let's say the example will be heating. Okay. Now, when we click save, the software asks me what is the data for the tank. Now we need to use jacket tank. My tank, according to the example that I have here, okay, my tank is a minute. Sorry for that. Yes, my tank is this tank. So I will feed the data for the tank. Sorry, 1,200 and 1,357 liter. So I need to use this one, 1,300 and 100, 200 and 103. Okay, sorry, those 2 and 3. Okay, this is the, sorry. Okay, here's the total volume. Okay, we need to use, sorry for that. I need to change the time. It was with, now this will be okay. 100, 200 and 100, 300. And this is the volume. And the total volume that I have in my tank is 300. Okay. So we need to feed here 300. Okay, let's click OK. Now the software is asking about buffers. As you can see in our, sorry for that. I need this example. Sorry, I will explain. I will start again. Sorry. I use not the complete data. Sorry. Again, process new will be heating. Yes, heating 1. And now I need to use this tank. Okay, and the data for this tank is follow. Oh, now it's okay. 2,000 millimeter, 2,000 millimeter. The total volume that we have in our tank is 9268 liter, and the total volume that I want to mix is 7.6 cubic meter. 7.6 cubic meter. Now this is my tank. When I click OK, I have no buffers. According to the process, if you scroll down, you see we have no buffers. So I select no buffers and click OK. And after that, the software asks me about the impeller that we have. You can see we have different kinds of impellers here, and we can use. And if it is not inside the geometry, you can use alternative impeller in order to solve. We are able to calculate any impeller you want. In our example, we are using lighting multi-stage. So we need to use lighting 3 multi-stage. And now what the software asking me, okay, give me the data about the geometry we have into the tank. So we have 900 millimeter diameter and 3 stages. The distance between stages is 500, distance from 300, okay, 500, 300. We are using 120 RPM, and the motor power is 3,000, but it is your actual motor power, and it is the base to protect your equipment, your system, your shaft, and more. Once we click OK, the software asks me about the eye of the jacket, okay, and the area transfer. In our example, we have here, it is 2,800, okay, 2,800. And if I don't know the area transfer, if we click 0, 200, yes. What is this? Let me check 1 minute. Okay, so it is no. Okay. Okay, if you click 0, the software calculates for you the heat transfer area. Okay, yes or not is not important for me now. Now, once we finish all the data, we need to fit the density and the viscosity of the media. In our case, I will use water. It is 1000 and the viscosity will be 1. And once you click OK, the software is able to start to calculate what we are looking for. As you see, this is the density and viscosity. And now it is my tank, ready to use. What we can do, of course, is to calculate the mixing power or many other parameters. For instance, I calculate mixing hydrodynamics. You see all the data, the distribution, the Reynolds number, and more. We can see in 3 dimensions what we are doing here. Yes, here in 3 dimensions we can show how is the fluid elements moving in our tank. Okay, you can see it here. We can illustrate more about how is the mixing here. It's not so axial, it's very radial. And we can reset and put the material in the top. This one, select another one here from the bottom, and we can see how is the interaction between the material in the tank. Okay, and you see that it's not so good. The solid distribution will be here a problem. Okay, and let's progress. Now, what we can do, if we can calculate the vortex if we want, but I want to go directly to the heating and cooling because it was my problem. You see, heat transfer. What we need to do is to ask the software the temperature in the heat transfer for heat transfer chemical reaction and temperature for a process that is batch and was heating with vapor. Okay, so what we need to do is to come to calculate heat transfer vapor agent and ask, for instance, what is the temperature of the tank. Now, the software asks me, you have reaction? Yes. You have the Reynolds number? In our case, we have. And the Reynolds number is 1E17. It is very fast, you can understand. Okay? And the energy of activation that we need is 1.255 E5, 1.255 E5. The limit, the lower will be 10 degrees, the maximum will be 125, and the heat release of the complete reaction it's 9E4 joule per mole. Okay, 9E4 joule per mole. Okay. Once we click OK, the software asks me, okay, what is your material? My material was stainless steel 302. The thickness, what we need is 8 millimeter, and we don't have fouling or and we don't know the mass. All of this we don't we will assume according to what we are looking for. So it's 8 millimeter. We don't have fouling. It's a new reactor, okay, like this. And if you don't know the mass, if you click 0, we calculate according to the data. And now we need the widthness of the jacket and the widthness of the wall. In our case, this will be 50 and 8, 50 and 8, and 8. And now click OK. Now the steam that we are feeding is in 100 degree according to our data in the sample. You can see. Okay, and now once you click there, okay, now you need to define what is the media that is you are moving. Okay, not only density and viscosity, we need heat transfer and heat conductivity. All the temperature was 20 degree, all the numbers that we provide 20 degree, and even you are going in very high temperature, we have internally changed this data according to some correlations we have inside the software. So the data that we have is 998, 1 centipoise. It's really water. Okay, so I will feed data for water, 4198, and 0.6. Okay, and now we ask to feed the initial temperature in the tank. Okay, and we assume that we have there all the mixture, reaction. So we have 20 degree. We need, and we feed 5 mole of the reagents. A plus B give me C. Okay, and I want to calculate during 600 seconds. And what you can see there, okay, when we are doing 20, 5, 5, and 600, okay, we show this here, okay. What will happen when we click OK, the software understands the number that you remember from the presentation, and when you click OK, you see that after 4.5 minutes, it's going up. You remember this number, okay, and you are going up. We know that we want to avoid it. So we need, for instance, now to avoid this situation. So how to avoid this situation? If to change. So let's say now that we change to cooling. So we'll go to calculate the cooling with water at 20 degrees and 40 cubic meter per hour. So if we go now and calculate batch, liquid, and calculate the temperature, now he asking me what is the media we're using in the jacket. So we use 20 degrees, and the velocity that we are using is 40 cubic meter per hour. 40 cubic meter per hour. Okay, and now when we click OK, now you see that this going in this way, but it is not enough, because we know that we need to change the other parameter, that is what was the initial concentration of our material and what was the temperature there. So we need to change this data. How to do it? We go to the software. You can change in the edit input the heat transfer and the batch situation to 40 degrees and 4.75. This is the time that you start to feed your cooling system. Okay, your cooling system start to work. Okay, and once you are applying it and you click OK, the software provides to you immediately the situation that you are really going to up, but now you see that it's not going to the end, it's going down. Of course, it is not advisable to do, but what I wanted to show to you that the software is giving you all the results according to what we are talking about. And if, for instance, I feed some solids, okay, and the density of the liquid is like this, and the concentration of the solid is like this, okay, and the solid density is like this, and the particle size is 300 to 500, okay, what will happen now is what we'll get is that complete suspension is questionable. So for this, we need to change the RPM. Let's say we are talking here about 85, okay, 120, so it's okay, but the particle size is very big. We need to reduce the particle size, change the density, and so this that I wanted to show to you some how to calculate. Of course, we have many things. For instance, I can have a process analysis, and I can have click here the heat the heating, and I can compare between them. Okay, I can compare between them if I want. When sent to you, this is another kind of operation that I can compare between softwares and generate tables with the results. So all of this we can do is more. What I wanted to show is showing I passed exactly, we passed the time, it's 1 hour. So thank you very much to be with us. If you want a tailored meeting with you, we'll be very happy to provide. And thank you to be with us. We will very happy to be in contact with you. Have a good time. Bye-bye.